All right, so we did some polar graphs before, so just kind of visualize as you're writing that down. Visualize the different polar graphs we did. So we're finding the area that's bounded by that polar graph. That's what we're kind of working with, okay? So definitely we're talking about things that aren't functions. They don't pass the vertical line test. Different pieces like that. You can remember some of the shapes that we did in class or you saw for homework. Okay, so just anything like that. So that's what we're finding the area of. The radial lines, alpha to beta, this is referring to the theta min, the theta max to complete the graph. So was the graph completed from 0 to 2 pi? Was it completed from 0 to pi? Did you have to go from 0 to 4 pi? Were you only looking at from pi thirds to 2 pi thirds, whatever? That's just what the angles we're looking between where that graph's created. Most of the time, we'll see it used like this with R. Because typically our polar form, we see it as R equals. We have that. But remember that if we had something like R equals sine theta, that is the same as using a function notation, f of theta, sine theta. Okay? We don't typically use the function notation because they're not all functions. But you can still use the notation because the basic function notation just meant, hey, whatever's in here is the variable in there. No different than before you had y and then f of x. So that's why you see both of these. Typically, this will be the most popular one. It'll have something in R along those lines. As far as evaluating the integral, we're going to evaluate the integral on our calculators just like we did before when we did area and volume and things like that. That's nothing new on that part. What you'd want to make sure of is your calculators in radians. That part you would want to make sure of when you're doing that calculation because typically these are in radians. So it goes by your angles. If your angles are in radians, make sure you're in radians. If your angles are in degrees, make sure you're in degrees. Those of you that are in physics have seen a lot of things in there in degrees. You flip back over to degrees a lot of times. So just make sure you're in the proper mode. As far as the evaluation, I think that's pretty simple because it's in your calculator. The setups are where we're going to have the problem or where the work's going to be. So let's take a look at this. We want the area enclosed by r equals 2 sine theta. Now this is where we're going to have to do a little bit of investigation. Here's the easy part of the setup. Area equals 1/2 integral 2 sine theta squared d theta. I say the easy part, the half's there, r is 2 sine theta, we got to get that squared. Now the difficult part comes in, or the part I've got to do some investigation on. I need my limits. Okay? And you can do this looking at the graph, you can do it by hand, or some of them you could do either way. Something like that. Okay? So let's take a look at the graph first. Okay, since we already kind of used to graphing, since we graphed last time, your calculator should already be in that polar mode. So you're just going to graph the generic 2 sine theta. You probably have it already set. I'm not sure what you finished on the last homework problem, but you probably have it set 0 to 2 pi or something like that, theta min, theta max. And the question is, when you look at it, okay, do you see a complete graph or not? If you don't, then that means you need to stretch past 2 pi. If you do, then maybe 2 pi is correct, maybe it needs to be less. Okay, so tell me this, do you see a complete graph when you look at it?
Yes.
Okay, so that means we don't need to go further to complete the graph. Right? So let's see if the graph started redrawing itself. So go back to your window. Instead of 0 to 2 pi, go 0 to something else and see where you get a complete graph. And you can play with it a few different times, put different values in. Start with 0. But 0 to what angle will complete the graph? What is it?
5.
0 to pi. And sometimes it can just play with it a little bit. You can kind of see, but it's completing back around that circle, right? So it would be 0 to pi. Now, another way. When you first looked at the graph, help me out here. Looks something like this, right?
Yes.
Okay. So it started right here at 0, or the origin, and came back to that. Everybody agree?
Yes.
Okay, what is the R value at the origin? How far is it away from the origin when you're at the origin? 0. So right here, R is 0. So it started when R was 0, and it ended when R was 0. Does everybody agree with that? So if 0 equals 2 sine theta, then sine theta is 0, and R is 0. So when would sine be 0? At 0 and pi. There's my limits. So a little bit of a combination, looking at the graph, working some by hand. You can mess around a little bit with the graph to kind of hone it in. You can also use the graph when I see this guy right here to help me algebraically. Go see what I've got. But there's my 0 to pi. So that's going to be where the work is. I think the setup, the half, and the R squared, that's pretty simple. There's not much to that. We're just getting that in. We got to find those limits, though. That's where we're going to have a problem. Okay? So that's some different things that can help us there. As far as calculating, it would be just entering this in. You can try it real quick to make sure you remember how to actually enter it. And all you need to do is make sure you're in radians, because we went 0 to pi, not 0 to 180 degrees. So that would tell me radians. But you should get 3.14. Cool.
So like my
Well, that would be the x's and y's. You got to set the theta min and theta max. Go back to your window. Let me see.
so that would work. Now I know what. Oh, that's what I did. Yep. I was like, wow.
But that would be just the left and right.
So I don't
We gotta find what's
You divide by two then. What?
3.14. In the middle.
Yes, it's a Sunday.
What?
You thought I was going to go down. I like your English.
Daylight savings time too.
Wow.
Daylight savings time.
Right.
Yes.
Farmers never use it. Farmers say daylight savings time before. It was used for work.
Well, how can you expect us to go to war with everyone?
It was used during war
We'll have to
time.
look it up. You can at least produce the graphs.
They never used so I'm trying to do that. I don't know.
Doesn't matter.
That's
That's just the left and right. You want it-
That's
I usually break
I
it 7 to 10 and -7 to 7. That's why I always use the standard like.
Yeah, I was like, I need like.
So I guess we decided.
There's a lot of things just always be.
And then I
I
mine was
And I like how it connects like
what made the mistake?
It's because on mine.
I say just leave it on.
He tried to work.
If I go over, we'll figure it out.
He does like, you still get somewhat predictable.
Whole
year.
When I go to window,
It'd just be different things. Yeah, but he's
see my data man.
Why we have it.
Data
Well, it's Friday, if we're sleeping over Thursday,
But we could use still.
there's no way
I'll just gotta figure
No, I'm finding
Then when I go to
So you're
R
just looking to
equals,
see if you can
Yeah.
I know, so I was
I thought about that, I was like, I'm gonna have to.
We need to figure out where to change your thing.
So I'm not just like.
But again, the main picture showed you this. You can kind of see where the pieces are combining. Okay. All right, here we go.
They're just regular puppies, it's okay. They're just silly.
Let's go. Area bounded by r equals e to the theta with 0 less than or equal to theta less than or equal to 2 5/3. So this one got even easier than the last one. Why is that?
Because now we have limits.
We have the limits. We don't need to go find them. That's what made it easier. It looks worse because of that e. But the setup's pretty quick. We're going to go 0, 2 5/3, e to the theta squared d theta. All right, and let's make sure you can get this one. I jotted down 16.2. Let's see if you get that.
So when we plug into your calculator, we just use X.
Yeah, it doesn't know the difference.
Because in for one thing.
Yeah, you just use X when you're putting it in because it just needs a variable there.
Or you can get it at it. I got it.
I forgot.
Is this the only thing we're learning today?
Yeah.
Wait, only the area? What?
So they're like double weapons.
We're gonna
So our
have
like
fucking finding some sort of round cylinder. It's
Yeah,
triangle.
ours was yesterday.
What? Ours like was yesterday?
No, it was the day before.
Yeah, but I was comparing
Hey, hey, you'll be fine. You'll be fine. Okay, we agree 16.2?
Yes!
Okay.
Yeah.
I'm getting the wrong thing.
Are you getting 32?
Did you times it by a half?
Oh,
Yes.
oh. Did you remember the square?
Yes.
What did you put it into?
2 pi over 3, 0 on the bottom, and I put an e to the theta square.
I might just have to add more parentheses somewhere.
Yeah.
Alright.
It might just be.
Go have the parentheses instead of white. That's what I put.
Is your calculator a radius?
Yes.
Your calculator.
Actually, we're stubborn.
All right, get that one down. I'll take a look at what's going on, Robert.
Oh dear.
I thought it said that.
That's what I thought.
Oh, interlude. I think all.
What plus square root of 2?
I thought it should be off.
No, that's, you don't want to square the theta, you square the entire e to the theta.
Oh. Okay.
So the
I need
square's in the
more.
right place. That makes sense.
Josh,
I'm just gonna
practice
because I want Yeah.
The square on the outside.
Like my life needed this right now.
Okay, now we're back to one that's tougher. All right, as far as what we've got to do. It says the inner loop, but let's go ahead and get down what we know. We're going to have a half integral 1 plus root 2 cosine theta, all of that squared, d theta. Okay. What's making it more difficult is the idea that it does say an inner loop, but that doesn't really matter. We'll be okay with that, okay? All right, so inner loop, and then when I graph it, I can see what an inner loop looks like. I have an idea there, but I've still got to figure out the limits. Okay? So if you haven't graphed it, graph it so you can visualize what that inner loop looks like. Got a picture.
So
Zoom in.
Very small.
So you might be really small. You have to zoom in to see the loop. So that means you need to extend your theta out, right? Didn't finish it. You're still on pi. Go back to 2 pi. Okay, so remember,
There we go.
Webb went here. He was still on pi, so it didn't finish it. So if you see it doesn't finish it, go back, extend it out. But sometimes you do have to zoom in to kind of see that loop. It's what you call a lemacon with an inner loop. It's a tough one.
Yeah, I have to.
Okay, so we got to figure out the angles.
Okay.
Everybody sees the inner loop, right?
Yeah.
Yeah.
Okay. Give me an R value where that loop starts and finishes. 0. Zoom.
But I figured it out.
You figured it out? Okay. So everybody agrees the loop's starting, it's going through that 0, the origin, right? And remember, if it goes to the origin, the R value is 0. Everybody agree with that? Makes sense? So let's set it up. 0. 1 plus root 2 cosine theta.
Yes.
So that would be negative 1 over root 2 equals cosine theta. And there's nothing wrong with negative 1 over root 2. You're probably used to seeing this as negative root 2 over 2. You're used to seeing it rationalized, but it doesn't matter. Okay. Okay, so if I've got a root 2 over 2, what special angle does that signify? Pi fourths. Where is cosine negative? Third and second. Third and second. So that'd be 3 pi fourths. 5 pi fourths. Now let's not think too hard here. Why did I put 3 pi fourths on the bottom? That's the smaller one. We go from the smaller to the larger. That's not new to us. And I wrote down 0.0708. See if you agree with that.
Yes.
No, I
So we can see as you're doing that, it does get more difficult when you have to figure out the limits. Okay. They're not hiding though. Usually you can look at the graph, tell what the R value is. If they're not special angles, something like this, well, you can go back to using that inverse function to find the angle. Like that's fine. Okay. If we're going to solve for it, this one just ends up being a special one. All right, now we saw the rose graph last time, or with the petals on it.
Oh, yes.
Okay, so let's look at something like this. Area of one petal for R equals 4 sine 3 theta. All right, so now, before I get to the graph, I can quickly get to 1/2 the integral 4 sine 3 theta will probably need to be in parentheses on your calculator. Squared d theta. I can get that part of the write-up pretty quick. Now there's 2 ways to look at this one. First, graph it. Let's see what we're looking at here, what we're dealing with. When you're looking at a graph, watch it graph. Now, here's the question. How many petals are there?
Three.
3. What do we know about each of the petals? They're all the same. I mentioned that last time. Sometimes they look a little bit different because your screen's rectangular. Sometimes they get skewed a little bit, but they are all the same. Okay? There's two ways of doing this. Number one, you graphed it, I'm assuming, from 0 to 2 pi, and it completed all 3 petals. Is that right?
Yeah.
Okay. Did it do it twice?
Yeah.
Okay. So 0 to pi completes it. Is that right?
Yeah.
Okay, 1 cycle. All right, so we've got to figure out what completes 1 cycle, right? So when we graph it, if it doesn't complete it, extend it out past the 2 pi. If it does complete it, drop it down. Some of you may have already been still in 0 to pi from a previous one, right?
Pi doesn't complete it.
Yeah,
Yeah,
like pi is close to
almost.
complete, but
What?
it's actually close. Which I don't think so.
I think it's just like approximately.
I don't know, mine's complete.
Yeah.
Mine's just close.
Like,
Well, it is. This is coming into 0.
Yeah.
Just zoomed in.
It's
It's not
just
stopping.
right, so
Yeah, it
it's right, mine's just close.
So pi would complete it. Now here's one thing you can do.
Okay, it's definitely not completing it. Like, look at this. It's separate. This is when it's pi. It's not.
It is completing it. It's got to the axis. It's trying to go through.
Oh,
You're zoomed in too far.
all right.
So zoom out, we can see. It's getting close, so it's kind of tying into that axis. Zoom out some. All right. 0 to pi would be everything, right? Everybody agree? Okay.
Boom.
Divided by 3. Because they're all 3 the same.
And the answer is
The other way of doing it is the R value was at 0 where it finished the pedal, right? Started and finished the pedal. Okay, so let's look at another way. If my R value is 0, 4 sine 3 theta, so that'd be 0 sine 3 theta. So this would be when 3 theta equals 0 or pi, which that'd be when theta equals 0 or pi thirds when you divide everything by 3. So you could rewrite it as 1/2 integral 0 to pi thirds 4 sine 3 theta squared d theta, and you'll get the same answer. The nice thing about the flowers, if I see how many petals there are, I can always do the whole thing and divide by how many petals there were, and I'll get each one. So if I had graphed this thing and there were 8 petals, I'd divide by 8. Okay. Yes, you can go figure out what 1 petal is, and it works great. Okay. But this can kind of save you a little bit of going through this. Okay. Both are correct. Oh, this is referring back to what we did before. This is using the realization that they're the same amount each one. Everybody okay there? Okay, on one of the homework questions you're going to have to look back at a formula for, where am I at? Arc length. Yeah, find the length of the curve. You're going to have to look back at a formula of the arc length in the section. Okay? It's just, again, following the formula. You won't have to know any of the formulas for the test. Okay? You'll have access to them.